The morning of August 12, 1944, a modified cable-laying ship called HMS Latimer sits anchored off the coast of Sandown, Isle of Wight. Below deck, in a space that once carried telegraph cables, rests something entirely different. 90 miles of 3-inch pipeline, coiled around an enormous steel drum, designed to do something that every petroleum engineer in Britain had declared categorically impossible just 2 years earlier. The ship's captain checks his watch. 0600 hours. In exactly 4 hours, his vessel will begin unwinding this pipeline across 70 miles of open ocean, through waters prowled by German submarines, past unexploded mines, to connect Britain's fuel reserves directly to Allied forces fighting in France. If the pipeline works, it could deliver enough fuel to power hundreds of tanks, thousands of trucks, and countless aircraft. If it fails, the entire invasion could stall, giving German forces time to regroup and push the Allies back into the sea. But here's what makes this moment truly extraordinary. This pipeline isn't just an engineering solution, it's a mathematical impossibility that one stubborn British engineer refused to accept. Because in early 1942, when military planners first asked if fuel could be pumped under the English Channel, every expert in the room gave the same answer. No. Absolutely not. The technology doesn't exist. They were wrong. And the story of how one engineer proved them wrong would change not just the outcome of World War II, but the entire future of undersea pipeline engineering. Let's go back to April 1942. Britain is in its third year of total war. The United States has joined the fight after Pearl Harbor, and Allied planners are beginning to sketch the outlines of what will become the largest amphibious invasion in human history. The numbers are staggering. Millions of men, thousands of vehicles, mountains of ammunition and supplies. But one number keeps surfacing in every planning meeting, haunting every logistics officer who studies it. 1 million gallons. That's how much fuel the invasion force will need. Every single day. Not for a week. Not for a month. For as long as it takes to push across France and into Germany. 1 million gallons daily, sustained indefinitely, delivered across 70 miles of the most dangerous water in the European theatre. The English Channel in 1944 isn't just water, it's a graveyard. German U-boats patrol these waters with lethal efficiency. They've already sent hundreds of Allied ships to the bottom. The mathematics are brutal. Each tanker destroyed doesn't just mean lost fuel, it means dead sailors, burning oil slicks, and Allied tanks sitting immobile on French roads while German forces advance. Even if tankers somehow made the crossing safely, unloading presents another nightmare. The invasion will destroy port facilities. The assault itself will crater docks, collapse piers, and reduce harbour infrastructure to rubble. Building new ports will take months. The Allies don't have months. Eisenhower knows that momentum is everything in amphibious operations. Stop moving forward for even a week, and defensive forces can establish killing zones that will turn the beaches into a massacre. So, in April 1942, Vice Admiral Lord Mountbatten, Chief of Combined Operations, sits in a London planning room and asks a question that will define Allied logistics for the rest of the war. What if we just build a pipeline under the ocean? The room goes silent. Not the thoughtful silence of people considering a brilliant idea, the uncomfortable silence of people wondering if their commanding officer has lost his mind. Mountbatten isn't joking. He's dead serious. He wants a pressurized petroleum pipeline stretching across the seabed, pumping aviation fuel and gasoline 24 hours a day while a war rages overhead. One advisor, a petroleum executive, with 30 years of industry experience, speaks for the room. That is the most ridiculous proposal I've heard in my entire career. Everything about this idea violates the fundamental principles of pipeline engineering. No one has ever built a flexible, pressurized pipeline that can survive months of saltwater immersion. No one has ever laid continuous pipe across 70 miles of open ocean. The water pressure alone will crush conventional pipes. Ocean currents will twist anything flexible until it tears apart. Saltwater will corrode exposed metal faster than you can pump fuel through it. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. And even if someone somehow solves all those problems, there's still the impossible question of deployment. How do you transport 90 miles of pipe across the channel without it tangling, breaking, or sinking the ship carrying it? The engineering challenges stack on top of each other until the entire concept collapses under its own absurdity. But Mountbatten doesn't give up. He contacts Geoffrey Lloyd, the Minister of Petroleum, and asks him to investigate whether this lunatic idea might somehow be possible. Lloyd, in turn, reaches out to Britain's major oil companies. Can anyone design a pipeline that can be submerged in the English Channel? The question lands on the desk of Arthur Clifford Hartley, chief engineer at the Anglo-Iranian Oil Company. Hartley is 53 years old in 1942. He's not young. He's not particularly famous. He's a practical engineer who spent the previous 2 decades solving mundane problems about moving oil from refineries to storage tanks. Nothing in his background suggests he's the man to revolutionize undersea pipeline technology. But Hartley has something more valuable than fame or youth. He has a peculiar combination of stubbornness and methodical thinking that makes him examine problems other people dismiss as impossible. When Lloyd's inquiry reaches him in June 1942, Hartley doesn't immediately say no. He says something that will prove far more dangerous to German logistics. Let me look at the numbers. Hartley begins with first principles. What makes submarine pipelines impossible? The answer, according to every expert, is everything. The pipeline needs to be flexible enough to coil for transport, yet strong enough to withstand enormous pressure. It needs to resist saltwater corrosion for at least 6 months. It needs to be heavy enough to sink and stay on the seabed during storms, yet light enough to handle aboard ships. It needs to maintain structural integrity while pumping high-octane fuel at pressures that would burst conventional pipes. These requirements contradict each other. You can make pipe flexible, but then it won't withstand pressure. You can make it strong, but then it won't coil. You can protect it from corrosion, but the protective coatings add weight that makes deployment impossible. Every solution creates 2 new problems. It's an engineering paradox with no apparent resolution. Hartley attacks the problem from an unexpected direction. Instead of trying to design a pipeline from scratch, he looks at what already works in hostile undersea environments. Submarine telegraph cables. They've been crossing oceans since the 1860s. Someone, somewhere, already solved the fundamental problem of protecting metal from saltwater corrosion for extended periods. He obtains samples of submarine telegraph cable and dissects them layer by layer. The design is elegant, multiple protective layers, with lead sheathing providing a waterproof barrier. The lead doesn't corrode in saltwater. It can be extruded into long, continuous sections. It's naturally flexible. But telegraph cables only carry electrical signals. Hartley needs to carry pressurized fuel at thousands of POs, gallons per minute. The engineering challenge is exponentially more complex. By late summer of 1942, Hartley has assembled a small team: metallurgists, welding specialists, marine engineers, all sworn to absolute secrecy. They work in isolated facilities, often not knowing what other teams are developing. Hartley visits each group, collects their findings, and synthesizes solutions like pieces of an enormous puzzle. The pressure is crushing. Every week brings new demands from military planners who don't understand why this is taking so long. Every test reveals new problems, and the clock keeps ticking toward an invasion date that waits for no engineer. Some nights Hartley barely sleeps, running calculations in his head, wondering if he's chasing a fantasy that will waste resources Britain can't spare and cost Allied lives when it inevitably fails. But he keeps working, because the alternative, sending tankers through U-boat-infested waters, will certainly cost lives. At least his pipeline offers a chance. By autumn 1942, Hartley's project has earned its code name, PLUTO, Pipeline Under the Ocean. The name is deliberately vague, designed to confuse German intelligence if they ever intercept communications. To anyone outside the inner circle, PLUTO could mean anything: a new weapon system, a radio code, a logistical designation. That ambiguity is intentional. Churchill himself has taken personal interest in the project, and anything Churchill cares about gets the highest security classification possible. But clever code names won't solve the fundamental nightmare Hartley faces. His prototype pipeline needs to accomplish things that violate the known properties of materials. It needs to flex like garden hose but withstand pressure like battleship hull, 3 inches in diameter, capable of handling pressures up to 1,500 pounds per square inch, resistant to corrosion for months of continuous saltwater exposure, light enough to coil onto massive drums for transport, yet heavy enough to sink to the seabed and stay there during channel storms. Hartley's team begins experimenting with lead alloys. Lead has advantages. Natural corrosion resistance, can be extruded into continuous sections, sufficient flexibility to coil without cracking. They develop a design with a 3-inch steel core for structural strength, wrapped in lead for corrosion protection, then reinforced with more steel, and finally sheathed in another layer of lead. The result looks like an enormous industrial cable, about as thick as a man's thigh. It weighs approximately 55 pounds per foot. 1 mile of this pipe weighs over 290,000 pounds. Now comes an even stranger problem. How do you transport something that heavy and that long without sinking your ship? You can't just coil it in a cargo hold. The weight would break the pipe itself. Hartley's solution is genuinely radical. Wind the pipeline onto enormous floating steel, drums. Each drum 40 feet in diameter, 1,600 tons when fully loaded with pipe. These drums, nicknamed conundrums, would be towed across the channel by tugboats, slowly unwinding pipeline to the ocean floor as they go. Think of it like the world's largest and most dangerous fishing reel, but this creates another engineering nightmare. As the drum rotates and releases pipe, the pipeline will naturally spiral and twist as it sinks. Twisted pipe means kinked pipe. Kinked pipe means ruptured pipe. Hartley has to calculate the exact rate of unwinding, the precise weight distribution, and the ideal sinking speed to keep the pipeline descending straight and true. Get any variable wrong, and 70 miles of expensive, irreplaceable pipeline becomes 70 miles of useless scrap metal on the channel floor. The metallurgy pushes 1940s material science to absolute limits. Welders have to join lead sections without creating weak points where the pipe will burst. Engineers have to ensure the lead alloy won't react with petroleum products and contaminate fuel. Marine engineers have to account for tidal forces that will lift and lower the pipeline several feet twice daily. And all of this has to work flawlessly the first time. There will be no second chance. D-Day is coming, ready or not. Theory and reality are different things. In early 1943, Hartley's team is ready to test their first prototype in actual ocean conditions. They choose the Thames estuary for the trial run. Close enough to London for easy access, remote enough to maintain secrecy. Engineers load a shortened section of lead-wrapped pipeline onto a smaller test drum, tow it into the estuary, and begin unwinding. What happens next is every engineer's nightmare. The pipeline sinks beautifully for the first 100 feet, then it starts twisting. The lead sheathing, which looked perfect in laboratory conditions, begins buckling under combined stress of its own weight and water pressure. Within minutes, the outer lead layer tears open like wrapping paper. Salt water rushes into the gap between lead and steel core. The pipeline's internal pressure causes it to balloon outward. Then it ruptures completely, spewing test fluid into the Thames. The entire team watches in horror as months of work literally explodes before their eyes. They haul up what remains of the pipe. The post-mortem analysis is devastating. The lead layers separated from the steel core during unwinding. Welding joints failed at multiple points. The pipeline twisted far more than calculations predicted, creating stress fractures they hadn't accounted for. Even sections that didn't burst show signs of crushing from external water pressure. If they can't make it work in the relatively calm Thames estuary, how will it possibly survive the English Channel during a storm? Hartley goes back to the drawing board, but now he's working against an even tighter deadline. Military planners have tentatively scheduled the invasion for spring 1944. That gives him less than a year to redesign everything. His team tries reinforcing the lead layers with steel wire mesh. The pipe becomes too rigid. They experiment with different alloys that flex better. Those corrode faster. They adjust the drum unwinding mechanism to reduce twisting. The pipeline still kinks. Every solution creates two new problems. The failures keep coming throughout 1943. One test sees the pipeline sink too fast and slam into the estuary floor, cracking the lead coating in dozens of places. Another test has the pipeline float instead of sink because air trapped inside the steel core creates unexpected buoyancy. They add weight. It sinks too fast again. They vent the air. Water seeps into the core. It's like trying to solve a puzzle where every correct move scrambles three other sides. By mid-1943, some senior military officials are quietly suggesting they abandon Pluto entirely and accept the risks of tanker convoys. The project has consumed enormous resources, specialized steel, lead that could have been used for ammunition, engineering talent desperately needed elsewhere. One advisor calculates that Pluto has cost more than 3 destroyers. And unlike destroyers, the pipeline can't even float properly yet. The pressure on Hartley becomes immense. He's gone from Britain's secret weapon designer to the man who might have wasted millions of pounds on an impossible fantasy. But Hartley isn't ready to give up. He has one more radical idea, and it will require splitting his approach into 2 completely different pipeline designs, running simultaneously. Here's where the engineering gets really interesting. Hartley realizes he's been thinking about the problem wrong. He's been trying to create one perfect pipeline design, but perfection is the enemy of progress. Instead, he proposes developing 2 entirely different pipeline systems simultaneously. Let them compete. See which works better. Deploy whichever design proves more reliable. Military planners think this is wasteful. Why spend resources on 2 systems when one might work? Hartley argues, it's insurance. Better to spend extra resources now than watch the invasion fail for lack of fuel later. Reluctantly, they approve his plan. The first design keeps the lead alloy approach, but with crucial modifications. Hartley's team redesigns the core structure using refined layering techniques. They call this the HAIS pipeline. The name comes from the partnership, Hartley Anglo-Iranian Siemens. The lead provides excellent corrosion resistance. The new layering technique reduces twisting during deployment. Each section weighs slightly less than before, making the massive drums marginally easier to handle. But the HAIS design still requires those enormous conundrums, still needs perfect unwinding precision, still faces all the problems that plagued earlier tests. The second design takes a completely different approach. Engineers at Siemens Brothers and Iraq Petroleum Company propose using steel pipe wrapped in protective layers. Now, steel corrodes in saltwater. Obviously, but they have a solution. Wrap steel in layers of waterproof fabric impregnated with bitumen. Cover that in steel wire reinforcement. Add outer sheath of more bitumen-soaked fabric. The result looks less like pipe and more like industrial fire hose made of metal. They call this the Hamel pipeline, named after H.A. Hammick and B. J. Ellis, the chief engineers who designed it. The steel design has advantages. More flexible than lead, meaning less stress during unwinding. Steel pipe can be manufactured faster because Britain has more steel production capacity than lead refineries. If sections fail, steel is easier to repair or replace than lead alloys. But steel also has serious drawbacks. The bitumen coating can crack during deployment. Water seeping through even tiny cracks causes rapid corrosion. Steel pipe is more susceptible to pressure changes. Pump fuel too fast, and the pipe can rupture from inside out. Throughout late 1943, both teams work in parallel, each convinced their design is superior. Arguments erupt during planning meetings. Lead advocates point to superior corrosion resistance and proven underwater cable technology. Steel supporters emphasize manufacturing speed and battlefield repairability. Engineers literally take sides. The rivalry becomes intense. Hartley finds himself mediating disputes while simultaneously pushing both teams to solve remaining problems faster. Testing continues in the Bristol Channel. Now, with both pipeline types, the steel Hamel design shows promising early results. It unwinds more smoothly, shows less twisting. But then a test section develops a leak after just 48 hours of pressurized fuel flow. The bitumen coating failed at a weld joint. Meanwhile, the lead-Hise pipeline survives longer pressure tests but continues having deployment issues. The conundrum drums unwind unevenly, creating sections where pipe hangs suspended in water instead of resting on the bottom. By December 1943, neither design is fully reliable, and D-Day is now just 6 months away. Hartley needs a miracle, or he needs to pick the least bad option and pray it holds together long enough to fuel the liberation of Europe. The clock has run out. It's January 1944, and Hartley faces the decision that will define his career and possibly the outcome of the war. Neither pipeline design is perfect. Both have failed tests. Both have limitations. But the invasion is coming whether his pipelines work or not. He makes a choice that seems counterintuitive. Deploy both. The HAIS-led pipeline will go first, laid across the shortest route from the Isle of Wight to Cherbourg once Allied forces capture that port. The Hamel steel pipeline will follow, connecting Dungeness to Boulogne once those beaches are secure. 2 systems, 2 technologies, double the chance that at least one will work. Military planners are skeptical but approve the plan. They have no better alternatives. Tanker convoys will still be necessary, but every gallon delivered by pipeline is a gallon that doesn't require a ship crossing U-boat waters. Even partial success would save lives. The preparation that follows is staggering in scale. Factories across Britain work around-the-clock manufacturing pipeline sections. The Hase production requires specialised lead extrusion facilities, limiting output to roughly 5 miles per week. The Hamel steel pipes come faster, nearly 8 miles weekly, but require more careful inspection because the bitumen coating must be absolutely perfect. Specialised ships undergo conversion to carry the massive conundrum drums. HMS Latimer and HMS Sancroft, former cable-laying vessels, have their cargo holds ripped out and replaced with reinforced cradles capable of holding drums weighing over 1,000 tons each. New winch systems are installed, powerful enough to control the unwinding of pipe that weighs 55 pounds per foot. Meanwhile, pumping stations rise along the English coast, disguised as everything from ice cream shops to bungalows to gravel pits. One station near Sandown hides behind the facade of a seaside cottage, complete with fake windows and a painted door that conceals massive diesel pumps. Another near Dungeness sits inside what appears to be an abandoned warehouse. The deception is elaborate and essential. German reconnaissance aircraft photograph the English coast constantly. Any obvious military installation would invite bombing raids. The pumping infrastructure alone represents an engineering achievement. Each station contains multiple redundant pumps capable of moving fuel at pressures exceeding 1,000 pounds per square inch. Underground storage tanks hold millions of gallons of aviation fuel and gasoline, connected by buried pipes to the coastal launch points. Electrical systems, backup generators, fire suppression equipment, all of it constructed in absolute secrecy while maintaining the appearance of normal civilian activity. By May 1944, everything is ready. Mostly. The pipelines sit coiled on their drums. The pumping stations await activation. Thousands of personnel have trained for operations they barely understand, knowing only their specific tasks within a vast machinery of logistics. And then they wait. D-Day comes on June 6, 1944. The largest amphibious invasion in history crashes against the beaches of Normandy. But Operation PLUTO doesn't launch that day. It can't. The pipelines need secure coastline on both sides of the channel, and the fighting for France has only begun. Cherbourg remains in German hands. Boulogne is still 60 miles behind enemy lines. For weeks, Hartley watches the invasion unfold while his pipelines sit unused. The initial fuel supply comes exactly as planners feared, from tankers running the U-boat gauntlet and from portable fuel containers hauled across beaches. Losses mount. Ships burn. Fuel shortages threaten to stall the advance. Cherbourg finally falls on June 26th, but German forces have systematically destroyed the port facilities. It will take weeks to make the harbour operational. Hartley pushes for immediate pipeline deployment anyway. His system doesn't need a functioning port, it just needs a beach. On August 12, 1944, HMS Latimer begins unwinding the first Hayes pipeline. The morning is calm, visibility good, sea state manageable. Hartley isn't aboard. He's at a command post on the Isle of Wight, receiving reports by radio, unable to do anything but wait and hope. The unwinding begins at 0600 hours. The massive conundrum drum rotates slowly, releasing pipeline into the channel at a controlled rate. Divers have marked the planned route with buoys. Escort, vessels patrol for submarines. Aircraft provide overhead cover. The operation proceeds with military precision. For the first 10 miles, everything works perfectly. The pipeline sinks smoothly to the seabed, following the prepared route, showing no signs of the twisting that plagued earlier tests. Reports come back to Hartley every 30 minutes. Pipeline integrity holding. Descent rate nominal, no visible damage. Then, around mile 15, problems begin. The pipeline encounters an unexpected underwater ridge that wasn't on their charts. The pipe drapes over the obstruction, creating a high point where it should lie flat. Engineers debate whether to continue or abort. Hartley orders them forward. They can address the ridge later. Right now, momentum matters more than perfection. By late afternoon, the Latimer has unwound nearly 40 miles of pipeline. They're past the halfway point. The French coast is visible on the horizon, but the pipe has developed several high points where it draped over seabed irregularities instead of settling flat. These create potential stress points that worry the engineering team. Night falls. The unwinding continues by searchlight, a dangerous necessity that makes the ships visible for miles. Every sailor aboard knows their targets. German aircraft have been active in the area. Submarines could be anywhere, but stopping now would be worse than pressing forward. At 0300 hours on August 13th, the pipeline reaches the French coast near Querqueville, just west of Cherbourg. Divers connect it to a pre-positioned manifold that links to portable storage tanks ashore. The physical connection is complete. Now comes the real test. Pumping begins at 0800 hours. Engineers at the Sandown station open valves and engage the massive diesel pumps. Thousands of horsepower push fuel into the pipeline at carefully controlled pressure. The fuel enters the system at one end. Now everyone waits to see if it emerges at the other. The distance is 70 miles. At the planned flow rate, fuel should reach France in approximately 14 hours. 14 hours of not knowing whether the pipeline is holding or leaking or ruptured somewhere in the middle of the channel. 14 hours of watching pressure gauges and praying the numbers stay stable. They do. At 2200 hours on August 13th, 1944, fuel begins flowing from the outlet at Querqueville. Not much at first. Air in the system needs to purge. The initial flow sputters and surges. But within an hour, the pipeline is delivering a steady stream of gasoline to Allied forces in France. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The celebration is brief, because almost immediately, problems emerge. The high points created during deployment cause fuel to pool instead of flowing smoothly. Pressure fluctuations, stress, the pipeline at these locations. Within 48 hours, the first leak appears, then another, then 3 more. Hartley's team scrambles to respond. Divers locate the leaks and attempt repairs, but fixing lead pipe underwater is nearly impossible. The best they can manage is reducing pump pressure to minimize further damage. Flow rates drop from the planned maximum to barely a trickle. The first Hayes pipeline delivers fuel, but far less than hoped. Instead of the 1 million gallons daily that planners dreamed of, the initial line manages perhaps 50,000 gallons before the leaks become too severe to continue. It's not nothing. 50,000 gallons keeps tanks rolling and aircraft flying. But it's not the game-changing solution Hartley promised. Military officials who were skeptical from the beginning start asking uncomfortable questions. Has Pluto been a colossal waste of resources? Should they abandon the project and redirect efforts elsewhere? The pessimists seem vindicated, but Hartley isn't finished. The Hayes line was just the first attempt. The Hamel steel design awaits deployment, and the route from Dungeness to Boulogne is shorter, with better charted seabed conditions. More importantly, The High's deployment taught lessons that the Hamel teams have already incorporated. Boulogne falls to Allied forces in late September 1944. Within days, preparation begins for Hamel deployment. This time, the approach is different. Instead of giant conundrums, the steel pipe is wound onto floating drums called HMS Persephone and HMS Algerian, smaller vessels that offer better maneuverability in coastal waters. The first Hamel line launches on October 26th. It crosses the channel in a single continuous operation, reaching Boulogne in under 20 hours. And this time, the results are different. The steel pipe, more flexible than lead, settles into the seabed contours instead of draping over them. Fewer stress points develop. When pumping begins, the flow is steady and strong. By November, 3 Hamel lines are operational between Dungeness and Boulogne. By December, the number rises to 11. Each line delivers roughly 300,000 gallons daily. Combined output approaches the magic number that planners dreamed of years earlier: 1 million gallons. Every day, through pipes resting on the floor of the English Channel while war rages overhead. The HAIS lead design, despite its early problems, eventually contributes 4 operational lines from the Isle of Wight to Cherbourg. Improved deployment techniques, learned from earlier failures, reduce the leak problem. These lines never match Hamel performance, but they add crucial capacity during the final push into Germany. The numbers tell the story. Between D-Day and V-Day, Operation PLUTO delivers over 170 million gallons of fuel to Allied forces in Europe. 170 million gallons that didn't require tanker ships. 170 million gallons delivered without a single sailor dying in a U-boat attack. 170 million gallons pumped silently through pipes that German intelligence never discovered. Because here's the remarkable thing: the Germans never knew. Throughout the entire war, German intelligence failed to identify Operation PLUTO. They knew fuel was reaching France somehow. They bombed port facilities and attacked tanker convoys. But they never found the pipelines. The undersea cables were invisible to reconnaissance aircraft. The disguised pumping stations looked like cottages and warehouses and gravel pits. The code name Pluto revealed nothing. After the war, captured German documents showed that their logistics analysts were genuinely puzzled by Allied fuel capacity. How were the Americans and British keeping so many vehicles operational? Where was all the fuel coming from? The answer lay literally beneath their feet, in pipes stretching across the seabed that German submarines passed over, without ever suspecting. Hartley received recognition for his achievement, though not immediately. In the chaos of victory, Operation PLUTO became a footnote, overshadowed by more dramatic stories of combat and liberation. The engineering teams dispersed. The pumping stations were dismantled. The pipes were largely abandoned on the channel floor, too expensive to recover and no longer needed. But the technology survived. The techniques developed for Pluto, the methods for laying continuous pipeline across ocean floors, the systems for protecting metal from saltwater corrosion, the engineering principles for maintaining pressure across vast distances. All of this became the foundation for post-war undersea pipeline construction. When offshore oil drilling expanded in the 1950s and 60s, engineers reached back to Pluto for guidance. How do you lay pipe on the seabed? Hartley's team had solved that. How do you protect steel from saltwater? The Hamel design showed the way. How do you maintain pressure across dozens of miles? The pumping stations provided the template. Today, thousands of miles of undersea pipeline crisscross the world's oceans. Natural gas flows from offshore platforms to coastal terminals. Oil moves from underwater wells to refineries. Fiber optic cables carry the internet across oceans. All of this descended, directly or indirectly, from the work done by Hartley and his team in desperate wartime conditions. The English Channel crossing itself has been repeated. Modern pipelines connect Britain to continental Europe, carrying gas and oil through routes that parallel the original Pluto lines. Divers occasionally encounter remnants of the 1944 pipes, corroded but recognizable, silent monuments to an engineering achievement that helped win a war. Arthur Clifford Hartley returned to civilian engineering after the war, continuing to work on pipeline projects until his retirement. He received a knighthood for his wartime service and various engineering honours. But he remained characteristically modest about Pluto, deflecting credit to his teams and emphasizing that he merely applied existing principles in new ways. Perhaps that modesty contains the deepest lesson of Operation Pluto. Hartley didn't invent new physics. He didn't discover unknown materials. He simply refused to accept that a problem was impossible until he had personally examined every aspect of it. When experts said undersea pipelines couldn't work, he asked why. When they listed the obstacles, he addressed each one systematically. When solutions failed, he tried again with modifications. The pipeline that everyone said was impossible became the pipeline that delivered 1 million gallons daily. The project that military officials wanted to cancel became the project that saved countless lives and accelerated victory. The engineer that nobody expected to revolutionize undersea construction became the father of an entire industry. On that August morning in 1944, when HMS Latimer began unwinding pipe into the English Channel, Hartley had already spent 2 years being told he was wasting his time. Every failure had given his critics ammunition. Every setback had seemed to prove them right. But he kept working because the alternative was worse. Because young men would die in burning tankers if he gave up. Because the invasion might fail if fuel didn't reach France. The pressure must have been unbearable, the responsibility staggering. Every calculation carried the weight of lives. Every decision affected the outcome of history. And yet he persisted, through failures and criticism and doubt, until his impossible pipeline pumped fuel across the bottom of the ocean. That's what makes Operation Pluto more than an engineering story. It's a testament to what stubborn determination can achieve when focused on solving problems that matter. Hartley didn't have better equipment than other engineers. He didn't have secret knowledge. He had patience, methodical thinking, and absolute refusal to accept defeat until every option was exhausted. The remnants of his pipelines still rest on the channel floor, covered now in decades of sediment and marine growth. Most people crossing between England and France have no idea they're passing over the remains of one of the most audacious engineering projects in military history. The cottages and warehouses that hid pumping stations have long since been demolished or converted to other uses. The conundrum drums were scrapped. The specialized ships returned to civilian service, but the principle endures. When someone says something is impossible, ask why. When they list the obstacles, examine each one. When solutions fail, try again. And never, ever give up on a problem that matters, because the world needs people stubborn enough to solve the unsolvable. 1 million gallons. Every single day, pumped through pipes that couldn't exist, across an ocean floor, patrolled by enemies, to fuel an army that liberated a continent. That's the legacy of Operation Pluto. That's the legacy of one engineer who refused to accept that impossible meant impossible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.